Yeah, we can start, Akila.
Yes, sir. Good evening to one and all present here. It's give me immense pleasure to welcome you all for this webinar. Now I request Mr. H.R. Mohan, Chair Events IEEE Madras and Chair IEEE LMAG Madras, to welcome the gathering and introduce about the topic and also introduce about our speaker.
Good evening. On behalf of the organizing units IEEE Computer Society of India, ACM, and IEEE Life Member Affinity Group, I have great pleasure in inviting our esteemed speaker, Dr. Arunkumar Sampath, Principal Consultant and Industry Advisor at Tata Consultancy Services, Chennai. Members and my colleagues from the organizing units and the participants joined the meeting through Google Meet meeting platform and those watching the YouTube streaming. Software-defined vehicles are redefining automotive value creation by shifting from hardware-centric personalization to dynamic software-driven hyper-personalization. Enabled by centralized computing, zonal architectures, and over-the-air updates, software-defined vehicles transform vehicles into adaptive digital ecosystems that evolve with the user's behavior, mood, and context. Today's presentation will explain the need and benefits of hyper-personalization, recent technology trends, challenges, and opportunities. Dr. Arunkumar Sampath is a seasoned technologist and a strategic leader with 28 years of experience spanning in automotive, aerospace, and defense sectors. He is not new to us. He has delivered webinars and in-person expert talks organized by the organizing units at different occasions. Dr. Sampath holds a PhD from the University of Maryland, an MBA from Lawrence Technological University, and MS and BTech in engineering from Villanova University and IIT Madras. A prolific writer, Dr. Sampath has authored over 35 technical articles on emerging technologies and continues to share insights via LinkedIn and other platforms. This profile reflects a rare blend of technical depth, strategic foresight, and industry influence across next-generation mobility ecosystems. With this brief introduction, let me welcome Dr. Arunkumar Sampath to enlighten us on the hyper-personalization in software-defined vehicles. Over to Dr. Sampath.
Thank you, sir. Thank you. I will share my screen. Just give me 1 second. It's a little slow. It's taking a little time. Can you see the screen?
Not yet loaded, sir. I think it's getting loaded. Yes, sir. Now it's getting loaded.
Okay. Thank you. Thank you, everyone, for joining. Thank you, Mohan sir, for inviting me again. I delivered a lecture about a year ago, so it's been 1 year since I've been here. This time, the topic is one of the hot topics in automotive. It is called software-defined vehicles. The purpose of the evolution of vehicle development is previously the OEMs used to control the vehicle development with respect to requirements, what is it that they want, the features, etc. So they used to share the requirements with the tier 1, tier 2 suppliers, etc. And then the rest of the ecosystem used to follow. And then, the vehicle development, the different components, hardware, software, etc. used to be done. The challenge is, number one, for every little feature addition or change, you have almost like 100 ECUs, 100 plus ECUs in a vehicle, whether it is a HVAC system or a steering system or advanced controls or electronics or whatever. So the complexity increases significantly, number one. Number two, if you have to make even a small change, the interdependence of one ECU on the other ECU is very high. Number three, usually there is a challenge as to who owns the data and who owns the IP and who owns the, any change that needs to be done. So the number four is, if an OEM wants to change the vendor, it is a little more complex because most of the information is residing with the tier one supplier, etc. So the OEMs do not exactly control the information or the vehicle development features and things like that. So these factors have enabled the automotive industry to evolve towards what is called the software-defined vehicles, where the software will be able to define the features. For example, let us say you buy a Samsung phone, whether you buy it in Middle East or whether you buy in China or Korea or India or Japan or US, the hardware pretty much remains the same. For example, if you say Galaxy, a specific Galaxy phone, it pretty much remains the same. It is primarily the software, the language, the features, etc., that you customize. For example, if you want French, you can do French. If you want Tamil, you can do Tamil. If you want to, English, you can download English, etc. So, and if you want a specific wallpaper and things like that, you can customize your phone. Something very similar with respect to the software-defined vehicles. What they're trying to do is they're trying to customize it using the software and try to commonize the hardware as much as possible and also reduce the complexity. Because what typically used to take, say, 5 years or so, now it has been shortened to, let us say, 3.5 years. Now the 3.5 years also with the advent of AI, Gen AI tools, etc., and of course software defining multiple features, the automotive industry wants to turn around much faster, something similar to what the mobile industry has been doing. Okay, so that is the purpose. Can you see the second slide, please? Can you see the second slide?
Yes, sir.
Yeah, okay. So this is pretty much the outline. What I will do is I will touch upon the software-defined vehicles, then the market trends, then even in like a technology readiness level for what is called the TRL for automotive, or let us say startups, there is something called SDV levels in the automotive. So how the supplier and the OEM ecosystem is evolving, I will have a slide on that. Then I will specifically touch upon digital twins, because what you're trying to do is if you have to minimize the development time and if you have to speed up the development process, you have to essentially mirror the physical system into a digital system. And how do you play with the digital, or how do you modify the digital so that you could have multiple permutations, combinations of changes digitally instead of physically, so that your prototyping, your validation, etc., the time and the cost and the prototyping costs, etc., are significantly reduced. And so in this context, you understand the evolution of the EE architecture, electrical electronics architecture, how it is evolving. As I said, the software architecture is also evolving. It is going towards what is called the modularized software-oriented architecture. And then the evolution of the software and the technology stack, I will touch upon that briefly. Then, of course, future topics means how the future aspirations are the focus topics. Because SDV, like other subjects, is a vast subject. So every company, every player cannot play everywhere. So different organizations focus on specific topics, and we at TCS are focusing on specific topics so that we could offer our specific services in those topics. And of course, we have specific future aspirations once we build a specific amount of capabilities in these focused topics. Then I will touch upon the core of this particular presentation, for example, the digital twins and virtualization, and how that is assisting towards federated learning. And why is hyper-personalization important? It is important because these days, for example, in a family, if you look at there are, let's say, 4 members in the family, you look at 4 different mobile phones, every single mobile phone is different in the sense, even though the hardware could be same, the software is different. In the sense, the features are different, how they, the games are different, the way the wallpaper is different, how they organize the files, etc., are different. So similarly, in a vehicle, for example, let us say there is a family car, you can also customize the family car. For example, if the husband and wife are sitting in the front and 2 kids are sitting in the back, you can always customize with respect to climate control, with respect to in-vehicle infotainment system, so many things. In addition to that, what the customers are doing these days is essentially, if they want feature on demand, let us say you have in TV, you have Netflix, you have Amazon Prime, etc. Wherever you want specific features, specific movies, specific shows or whatever, you can subscribe to them and you can cancel them. Okay, something very similar here. So how can you subscribe to a specific feature, or how can you cancel it depending on your whether you like it or not, or whether the subscription is over, etc. So that is where the hyper personalization comes into picture. But the biggest challenge is data privacy. Means whenever you are sharing information over a cloud or over a network, there is a chance that number one, the privacy is lost. Number two, there is a potential because your vector with respect to hacking is much higher. The hacking exposure is much higher. So you have specific challenges with respect to hacking and also data privacy. That's where the specific algorithm will come into picture, and that is what the federated learning algorithm is. Okay. Can you see the slide number 3, please?
Yes.
Yeah. So what you notice here is essentially how the industry is evolving, and what you notice here is essentially vehicle sales revenue are increasing, and the software as a component of the vehicle sale is also increasing. About 5-6 years ago, this number was less than 5%, let's say about 3% or so. Today, almost 14 to 15% of the software sales revenue in a vehicle is higher. In the sense, people want specific subscriptions, whether it is an autonomous driving, whether it is a specific feature on demand, etc., and whether they want OTA updates and things like that. Let us say you subscribe to LinkedIn itself. Even in the LinkedIn, you have, let's say, premium service versus basic service. In the premium, let us say you're looking for a job, you want a career change, etc. So you can sign up for specific features in LinkedIn. Something very similar in the vehicle also. When you purchase a vehicle, the software revenue as a percentage of the vehicle sales revenue is also going up. Okay. And what you notice is Tesla has been pioneering this, and what other OEMs have understood is, okay, if Tesla is able to increase their software revenue as a percentage of sales revenue year over year, why don't we also get into this bandwagon? That is where other OEMs started, for example, from Japan, from Europe, from China, etc. They also started jumping into this bandwagon, and they also started working on this. So essentially, what Tesla has done is they have done what is called the one-time charge for pre-installation. Then, of course, subscription services by the end of the year. Means if you want a specific a subscription, you can pay by month or quarterly or year, etc. And if you want specific upgrades, for example, if there is a specific bug or if there is a specific challenge in the vehicle, you can have what is called the over-the-air upgrades. Means you don't necessarily have to go to a garage. You don't necessarily have to leave your vehicle with a service technician for 1 or 2 days. You can get it done remotely when it is sitting in a garage or when it is sitting in a parking lot in your office or at your home. Okay, you can easily get that done. So this is evolving into what is called the Internet of Vehicles, because you have seen IoT, Internet of Things. Then it was IIoT, Industrial Internet of Things. Then it was IoE, means Internet of Everything. Now this is a specific subset of what is called the Internet of Vehicles, where the vehicles can talk to each other, and the real-time traffic updates, music streaming, etc. could be done. This is where the industry is evolving. Okay. Can you see the next slide, please?
Yes.
Yeah. So what you see here is essentially the global software-related automotive revenue, as I mentioned, it's significantly increasing year over year. And these are some of the players who are playing a big role. And you notice that NVIDIA is playing a big role, and it has tied up with multiple organizations. The who's who, for example, Robert Bosch, Continental, Aptiv, etc. They play a specific role in this ecosystem. And of course, Tesla has been a pioneer, but they are being given a run for their money by Chinese OEMs. For example, XPeng, BYD, etc. They are giving a tough competition to Tesla and Volkswagen and other companies in Europe, US, China, etc. So that is happening. So what you notice here is essentially 2 large markets are emerging. One is North America, of course. The other is the APAC. APAC includes India also, but essentially China, then Japan, then India. Then Europe is also, though it has pioneered with respect to electric vehicle adoption, the software different vehicles, there are different maturity levels for different players. For example, Volkswagen or JLR or Stellantis or Renault, etc. So different companies are at different SDV levels with respect to this SDV journey transition. I will touch upon that in the next few slides. So what you see here is, though Tesla has a lion's share, other guys are giving a tough competition to Tesla. Number one. Number two, OTA upgrades are being chargeable. Means if you have specific upgrades, etc., you have to pay for them. So the biggest challenge that the industry is fighting these days is what is called the cyber security challenges, cyber hacks. So this is where the technologies are evolving towards what is called the zero trust architectures, digital identity wallets, etc. So when you look at fintech, or when you look at healthcare, or when you look at automotive, for example, SDV, you notice that this zero trust architecture is pretty much the same. The application could be different, the data could be different, the data identification, etc., could be different, but the architecture is pretty much the same. It is a zero trust architecture. That means you just do not trust anybody, period. You just don't trust anybody. And every single ECU or every single feature or a software change, etc., it has to get authenticated. It has to be given specific access. There is absolutely no assumption being made, and you just don't trust anything. And even in the fintech, I mean, you are very well aware of the cyber crimes that are happening in India these days. So do not click on any link. Do not, be very, very careful with respect to phishing emails, WhatsApp messages, etc. So we are being very, very careful with respect to zero trust, with respect to fintech. So you have exactly the same feature being followed in the SDB, where if you have to prevent the cyber attacks, this zero trust architecture is being enforced. Okay. Then, as I said, data privacy of the customers is very, very important, whether it is a fintech or whether it is healthcare or whether it is automotive. So federated learning based algorithms are being implemented, where I will go into the details in the next few slides. This is being implemented so that the data privacy is ensured, the data transfer between a vehicle and cloud is minimized, and most of the computation, etc., is done through edge computing in the vehicle itself. So these are the technologies that are evolving. Okay. So as I said, different organizations are at different levels of maturity. So what you see here is essentially SDV levels. So what you saw in here, what you see here is essentially different organizations are at different levels. And when you go towards, let us say, SDV level, etc., you have pretty much decoupled the hardware and the software, and your software is pretty much driving the entire thing. And it will be hardware agnostic, means it will be chip agnostic, it will be language agnostic, and it will also be cloud agnostic, means it need not be tied to a specific cloud, let us say Amazon AWS or Google Chrome or Google Cloud or Microsoft Azure, etc. You're not exactly tied to a specific cloud. You're not tied to a specific chip, whether it is a Renesas chip or whether it is an NVIDIA chip or whether it is AMD chip. So you have specific layers that can easily talk to those different chips. If you have to change the chip, you can do it. So to that extent, the decoupling is achieved in SDV3. Whereas most of the companies that you see here, for example, Tesla, XPeng, BYD, Volkswagen, etc., they are primarily somewhere here, SDV2 to SDV3, somewhere in between. Of course, some other companies are actually on the lower side. For example, GM, I think to some extent Ford, and these guys are probably somewhere in the lower side of 2 here. Okay. So the ecosystem is evolving, as I mentioned at the beginning of this talk, that previously it used to be hierarchical and vertical top-down, where the OEM decides everything and everyone has to follow. For example, OEM says, I want a specific vehicle, specific feature, specific, benchmarking, and all those things, and they will drive the entire vehicle ecosystem, and the rest of the guys used to follow. Okay, and that is how it used to follow. But now it is what is called the collaborative co-development. The challenge for this is, as I said, number one, you may have about 100 ECUs in a vehicle that could be owned by Valeo or Bosch or Continental or Aptiv or Denso or any of these guys. So if you are an OEM and if you have to make a change, the Bosch will say, sorry, I'm not going to work with Continental. Or Continental will say, sorry, I will not work with Qualcomm. Or Qualcomm will say, sorry, I will not work with this guy. So you have a challenge that you have to manage the entire, interplay between all these players. You have to manage all this in the OEM. So that was the challenge, number one. Number two, the timeline was very, very high, number two. Number three, the complexity was high. Means even if you have to make a small change, you have to change many, many things. You cannot just segregate. And if there is a cyber attack, for example, there is a very good chance that it will spread very quickly through the network. So you cannot quarantine that attack. So the ecosystem is evolving towards what is called the collaborative co-development approach, where it is, instead of tier 1, it is moving towards what is called the tier 0.5, where the suppliers are working very closely with the OEMs in defining the requirements, in co-developing the systems, etc. So that is where the industry is evolving. Okay. And as you know, as you may notice, previously it used to be auto shows, whether it is a Frankfurt show or a Detroit show or a LA show or a Tokyo show or a Beijing show, etc. But now these are moving much more towards what is called the technology show. For example, CES, Consumer Electronics Show in Las Vegas, which is coming up from 6th to 9th in January 2026. That's where you can see all these players, all these OEMs, all these guys, etc. They are showcasing the latest in the technologies in the SDV domain, and of course other domains also. So moving from a traditional automotive show, it is evolving more towards a technology show. Okay. So as I said, because the ecosystem is evolving, you have to build a digital variant or a digital replica of the physical entity that you have. If you have to make the changes fast, and if you have to make multiple, modeling changes, etc. Number one. Number two, if you have to define the specific architecture, and if you have to give in specific updates, etc., it is also easy for you if you define the digital twins. So what different OEMs and suppliers are doing is, for example, if there is a powertrain, let's say battery or a motor, or let us say a vehicle control unit, etc., or if there, let us say there is a in-vehicle infotainment system, or let us say advanced driver assistance systems, or let us say autonomous driving or semi-autonomous driving. So even let us say there is a specific module that does the over-the-air software updates. So all these guys are trying to digitally build the ecosystem, replicating the physical actual entity in the vehicle, so that if they have to make specific changes, etc., it is being done very fast. Okay. And one of the things that is happening is what the hyper-personalization. Hyper-personalization is the focus of this particular topic, but there are other topics also that we can look at in the SDV ecosystem. Okay. So how is the architecture evolving? What you see here is essentially, before 2000, about say 25 years ago, it used to be what is called the distributed architecture. As I said, there used to be almost like 100, 120 ECUs in a vehicle. CAN and LIN-based communications used to have a body control module, dedicated sensors, ECUs, algorithms, and suboptimal computing power, etc. And complex wiring harness. The wiring harness used to be very, very complex, and of course, few kilometers. If you lay the wiring harness on the road, you can see that the wiring harness goes for a few kilometers. Okay. Sir, can you please go on mute, please? So how before 2020 it is evolving towards 2025 is essentially what is called the cross-domain architecture, where you are trying to centralize. Can you mute, please? Can you mute, please? It is moving towards a centralized cross-domain EA architecture, where you are trying to have multiple major domains. And from here, it is moving towards what is called the quasi-central architecture. And from here, this is where most of the OEMs are, whether it is a Toyota or whether it is BYD or Tesla or Xpeng, etc. So all these guys are somewhere here, and they are moving towards much more computing and much more hybrid vehicle cloud computing in vehicle, and then the central computing platform, etc. Essentially, what you notice here is from a power multiple ECUs, chassis multiple ECUs, etc. It is moving towards what is called the modular, means zonal. Let's say left to front, you have bunch of ECUs, etc. You have right from bunch of ECUs, etc. Left back, right back, and all. So if you have, let us say, 20 ECUs, 20 have literally gone down to 2 or 3 ECUs. So your complexity in an ECU has significantly increased. Your computing power requirements, etc., in an ECU has significantly increased with respect to the heat management, etc. It has significantly, the complexity of the architecture of the chip itself has significantly increased. However, the advantage is your complexity in the wiring harness has significantly gone down. Number one. Number two, if you have to, these guys can work independently of these guys can work independently of these guys, etc. Means all these zones can independently work. For example, let us say this is being done in Germany. Let us say this is being done in Bangalore. Let us say this is being done in Tokyo. So all these guys can work independently, and then they can, cross-check or communicate through what is called the central computing platform in a digital world. So you are not constrained by teams sitting in one place, or you're not constrained by, let us say these guys work with a specific hardware vendor. Let us say there is a delay, there is a challenge, but these guys don't have the challenge. So these guys can go ahead and work irrespective of what these guys are doing. In the sense, you are not constrained. Whereas here, if something here it doesn't work, then the rest of the guys are also affected. Okay, you remember during COVID time, we had a challenge with respect to chip availability, and there was a huge worldwide crunch with respect to automotive production and other productions, etc. Now all those things will be minimized. So even if there is a challenge here due to global supply chain or geopolitical issues, etc., the other guys can easily do their work. And if there is a specific bug that these guys are unable to solve, etc., so the other guys are not exactly affected and they can continue. So that is the advantage. So what you notice here is essentially the OEMs are moving towards what is called the L3+, the level 3+ autonomous driving, and the full stack development is happening collaboratively, and the OEMs are also trying to build their own cloud, what is called the private cloud. Means it is a combination of private and public cloud. Means public means whether it could be, let us say, Amazon cloud or Google cloud, etc. The OEMs, and of course OEMs are trying to build their own operating system. So the challenge is, on one hand you are trying to centralize, but on the other hand OEMs are trying to withhold some of the IP, and they are trying to have much more control with respect to operating system, hardware, software, and things like that. So it is still evolving. So how this is going to evolve in the next 5 years, we will see. Okay. So as I said, going from let us say legacy distributed architecture, where you have a bunch of aggregation of ECUs, in different parts of the vehicle, you have what is called the specific zonal, and then even the zonal is evolving towards what is called the cloud-based architecture. Okay, so that is how the EE architecture is evolving as you move towards software-driven vehicles. Okay. Now, what you saw previously was essentially at a vehicle level. Now let us understand what we are doing at a software level. Software level also, previously we used to have a specific software structure. It was little rigid, in the sense if you have to make specific changes, you had challenges. Let us say the cockpit and the ADAS have to communicate, and the ADAS has to communicate with what is called the motor control or a main control unit, etc. Sometimes you have a challenge that you can only work through the APIs, and the other things you may not be able to touch. For example, you have a middleware, etc. You may not be able to work with them, and you have to communicate only through the APIs. So and you can have an operating system here on the Linux, you can have a QNX, and you can have an AutoSAR, etc. So the multitude of operating systems, the multitude, this could be hardware, could be, let us say, a specific chip, this could be a different chip, and this could be a different chip. So if you have to work with a different chip here, then you are constrained, because this MCU can only work with this different chip. If you have to change the chip, then there is a huge impact on the development of this new MCU. So you are literally constrained by what you have, and you don't have the flexibility to make the changes. And the challenge is the OS could be different, the chip could be different. The APIs are the only things that are being opened. The middleware, you cannot make any changes, etc. So it was very rigid and complex. So the OEM said, look, this is not the best way. So it is evolving towards what is called the software, where they are essentially building the layers stack by stack by stack. For example, when you look at our UPS system, our Aadhaar-based UPS system, etc., it is essentially a stack by stack by stack. Even a uneducated woman, let's say 70-year-old grandma in a village, she can just use the QR code and she can do the payment. Why? Because JAM, Jandan, Aadhaar, and of course your payments account. Everything is related, and you have multiple players playing at different levels, and it seamlessly communicates, and it works. So if our UPI and our Aadhaar-based payment system, etc., is able to work, it's essentially exactly the same concept. What they're trying to build in a vehicle now. What they're trying to do is, whether it is a different chip or whether it is a different driver, they are trying to commonize wherever possible. And even if I have to work with, let us say, a Linux or a QNX or an AutoSAR, the OEMs are essentially working on only the interface layer. Okay, only this interface layer changes. For example, if I replace the Linux with the QNX, I don't have to replace the entire system. All I have to do is only replace the interface layer. So the rest of the things should be able to work. So you are trying to build what is called the OS abstraction layer, hardware abstraction layer, etc., so that your time to make the changes, your time to development is significantly reduced. Okay, this is essentially what the mobile ecosystem. For example, if you have to introduce a software, or if you have to give an upgrade in your, let's say, Samsung phone or an iPhone or other phones, this is exactly what they follow. So the automotive industry is also trying to follow the same approach. Okay, so it is evolving towards what is called the software oriented architecture. Means you are trying to decouple the applications and platforms. Means you can, let us say, in a smartphone, you can always download an app, you can always delete an app or play with the app, etc. So something very similar you can do it. Of course, the challenge is cybersecurity. That cybersecurity challenge is always there, but we will come to that later. Okay, but there is a flexibility here. Okay, so what at TCS, what we're doing is, we are not going to work on everything. As I said, in the ecosystem, in the full vehicle life cycle, there could be 100 different things that we could try. But what we're trying to do is essentially focus on our strengths. For example, digital twin is our focus. Virtualization is our focus. For example, let us say in the steel industry, or in the chemical industry, or in the healthcare industry, or in the, let's say, logistics industry, TCS has been doing excellent work, or even in the airlines, let us say MRO, logistics or whatever. So we have been working very closely with multiple different organizations, cutting across different industries, and we have built the digital twin of a boiler. We have built the digital twin of a chemical process in a healthcare industry, etc. So we are trying to do something very similar, digital twin of a specific. I showed you the previous slide. For example, a in-vehicle infotainment system, or an ADAS system, or a powertrain system, or a battery system, etc. So we can always build a digital twin for that, and then we can build the virtualization environment, and then we can define the software development cycle. That's exactly what TCS is trying to do. Okay, this is where we are working with different customers, whether it is a supplier or an OEM. This is where we are focusing. And as I said, with respect to hyper personalization, because the industry is evolving towards what's called the over-the-air software updates, and of course feature on demand, and different people want different things. So hyper personalization, you have a challenge with respect to data privacy, computing, and also subscription based, means the software revenue. So because of these reasons, the federated learning is being implemented to push for hyper personalization. That is also happening. As I said, because everything is working in what is called a collaborative environment, if you have to make specific changes, there has to be transparency. And if there are specific challenges with respect to any cyber attacks, etc., you need to understand what is the vulnerability, where is the vulnerability. For example, I don't know if you have been reading the news, there is something called an Nexperia chips. Nexperia chips, there is a challenge between Netherlands and China now. And because of that, Volkswagen in Germany is getting impacted, JLR in UK is impacted, etc. So supply chain insights, if you are able to understand what the supply chain challenges are, you are able to, through what is called the software bill of materials, you can be prepared with respect to any shocks or any surprises. You're a little prepared for that. Second thing is, with respect to cyber attacks, if there are specific vulnerability areas, you are able to figure that out, and you can build a firewall, or you can build specific access control and zero trust architecture, etc. So this could also be done. The third thing is, what we're trying to do is automated compliance. Lots of times you notice that when the software is before it is released, it has to be tested. And of course, no software is 100% bug free, and no software is 100% foolproof. So there is as much as possible with respect to standards and regulations, we ensure that the software is compliant, especially with respect to safety. Let us say you make a change in a steering system or a braking system, or other things, a powertrain, etc., which may have a significant impact on the safety. So there has to be automated compliance, means it is not manual anymore. You cannot say some developer sitting in China or some developer sitting in Bangalore forgot to do a specific test case, and we made a mistake and we released the software. Sorry, those days are gone. It has to be, these automated tools are available, compliance tools are available, and it has to automatically check through the CI/CD pipeline to the DevOps, DevSecOps, etc., and then it is released in the system. So that is also being done. Here, as I said, future aspiration for TCS itself is moving towards the zonal architecture as we move towards, as the OEMs and the suppliers move towards it. And we are specifically working on zero trust cybersecurity solutions for different customers right now. As I said, whether it is a fintech or a healthcare or automotive, we are exactly working on this. And depending on the customer, the applications are different, the use cases are different. Okay, so let us say you release the software and there is a challenge in the vehicle. Let us say you have sold already 100,000 vehicles. Now you have to do what is called a vehicle recall, or you have to fix the bug in the field. So that's going to be a very big change and be a very big challenge. It is going to be costly. It is going to be, you have your vehicles could be running in multiple states, multiple locations, multiple countries. So how do you make sure that you will make those changes? So there is something called a failed operational automotive software design. Means you are trying to minimize the damage, and you are trying to go back to a default system if something goes wrong. In the sense, let's say you release a software, let's say version 2.0, but there is a bug or there is a specific challenge. So if you want to go back to version 1.0, you can still do it. Means fail operational automotive software design using what is called the agent-based graceful degradation. This is exactly where the AI agents or the agentic AI comes into picture, and they make sure that specific steps or specific process in the process flow are followed. And if there is a specific issue, immediately that agent will raise a red flag, and you can stop right there, or you can back up. Okay, so those things are also being built in the software design. Then the third one is what is called the microservice isolation. As I said, in the zone, if there is a, let's say, left front, left rear, etc. If one of these guys are having specific challenges, you can always do what is called the microservice isolation, so that the other guys could easily continue. They are not exactly impacted by this. So you have what is called the runtime resilience for in-vehicle apps. Means you are trying to segregate them, and you are trying to lessen the impact if there is any challenge. Then another thing is what is called the predictive fault detection. Means let us say you have seen, you have come across a bug, or you see that something is going to fail. Then you have what is called the AI-based predictive fault detection. And how do you make sure that you do what's called a self-healing? Means you should be able to correct itself. So that is also being tried in the future. Okay. So as I said, digital twins for SDVs are going to be very critical, and so you can have multiple aspects of digital. Means essentially from a physical space, you are going towards what is called a virtual space. Using the data, you build the model, then you have a feedback, and then you improve the model, etc. So this is an iterative process where the model is iteratively built. It could be for the systems, it could be for the subsystems, etc. But you are trying to focus on multiple aspects. For example, real-time vehicle dynamic simulation. Okay, let us say you are testing a vehicle in a test track, and the test engineer says, look, I'm not happy with specific performance. Maybe the braking is not good, maybe the suspension feel is not good, maybe the steering is not good, etc. So an engineer sitting in let us say in a tech center can remotely check the performance, because through the cloud he or she able to download the data, check the performance, make the software tweak, etc. Again release the software to the vehicle, so that the vehicle could change the performance dynamically in the test track. So that is also being possible through the OTA updates and the digital space simulation. And as I said, highly automated driving. This is where moving towards the semi-autonomous driving. Lots of path planning, etc. are being done. So this is where the OEMs and the suppliers are working on. For example, Google has Waymo. Amazon has recently introduced its robot taxis in US, where they are able to deliver, for example, e-commerce delivery, etc., using drones and other things, using vehicles. So it is being done through what is called the highly automated driving and path planning. And as I said, most of the, let us say the vehicle is running, and let us say you are a e-commerce. You are supplying to different parts of within Chennai itself. For example, let us say you are trying to supply to different parts. Let us say your Blinkit or a Market Basket, or one of these e-commerce 10-minute delivery. You have a challenge in, let us say, Valasarvakam, which you don't have, let us say, in Vadapani, or let's say in Vadapani you have a challenge which you don't have in Adaya. So how do you make sure that you do what is called the edge computing, intelligence at the edge, and dynamically take specific decisions on the vehicle itself? Okay, so that is also possible. And you can do what is called the autonomous vehicle ops. And as I said, predictive maintenance. Predictive maintenance can be easily done using AI-based algorithms using the data that is produced by the vehicle. So this is also being done using the digital twins. So you have essentially product digital twin. You can have what is called a process digital twin. You can also have what is called a performance. You can also have a behavior. For example, let us say you have e-commerce vehicles. Let us say you have 1,000 vehicles. Let us say you are a Chennai call taxi. Okay, you have, let us say 250 taxis with you. You can easily identify which drivers are behaving how. Let us say airport side, how the taxis are being run. Let us say OMR side, how the taxis are being run. Let us say Ambattur side, how the taxis are being run, etc. So you can easily segregate the data using what is called the behavioral twin, and you can easily dice and slice the data into different aspects for data analytics. So that can also be done. Accordingly, you can model the behavioral digital twin. Then there's something called the cross domain. Let us say sometimes the in-vehicle infotainment, there is an impact on advanced driver assistance systems, or sometimes the powertrain has an impact on braking or steering, etc. So if you have to understand the impact of a specific change on the other system, you do what is called the cross-domain digital twin, where essentially you do a combination of physical and cyber. It's called cyber physical systems. You're trying to build the digital twin based on that, and you're trying to do the modeling and then do the simulation. So that is also being done. Okay. So coming to the core topic in this particular talk, previously we touched upon SDV levels, we touched upon evolution of EE architecture, then we touched upon how the ecosystem itself is evolving, then we touched upon digital twins, for example, product, process, behavior, etc. So here what I told you is, as the vehicle sales revenue is increasing year over year, the software content and the software revenue sales are also increasing as a percentage of vehicle sales. So because the customers want specific personalization, okay, and what works in, let us say, Tamil Nadu may not work in Uttarakhand, what works in Uttarakhand may not work in, let us say, Gujarat, etc. So if you are to personalize for that particular driver in that particular state, you can always, provide specific features, because Uttarakhand may have, very cold weather, Kashmir may have very cold weather, whereas in Chennai or, Kanyakumari, you don't have that problem. So you can always disable certain features. For example, in Kashmir, they want a heating. You don't necessarily need heating in Chennai or, Kanyakumari. So you can always disable that. So you can easily customize that particular feature, and you can personalize it for that particular vehicle, that particular driver, that particular family, etc. So the challenge, as I said, is the data privacy. So what you're trying to do is, as much as possible, you are trying to make the changes in the vehicle itself, okay, make the computing in the vehicle itself at the edge, and you are trying to minimize the data transfer to the cloud so that the latency is not compromised, the computing power is not compromised, the privacy is not compromised, and you are trying to make the changes in the SDV through these specific federated learning hyper-personalization. So that is essentially the architecture. And of course, one more thing is, let us say, as I said, if you are running vehicles in Kashmir, where there's a lot of snow and a lot of landslide, etc., your tire wearing may be much higher compared to, let us say, you are running in Kerala. Whereas in Kerala, it rains much more than in, let's say, Tamil Nadu, especially Chennai. So your tire wear in Kerala could be different, your tire wear in Kashmir could be different, etc. So how are you able to predictively maintain the tires? How are you able to predictively maintain the brakes? Okay, so you can do all of these things easily using the hyper-personalization and, of course, digital thing. You can do all. Okay, so what you see here is essentially the objective is to enable real-time privacy preserving. This is the key. Privacy preserving personalization of SDV features, because what you are doing, infotainment, etc., you may be listening to specific, stock market analysis, or, Hindi music or Tamil music or, English music or whatever, but you do not want, others to follow your privacy settings, etc. So you can easily mask them, and you can easily restrict the access. But at the same time, if you have to avail of specific ADAS features, you can also enable them. And if you, as I said, running a vehicle in Kashmir versus Kanyakumari is different. So the climate control features, etc., could be different. So you can easily enable some of those features using federated learning without sharing the raw user data. Means you don't necessarily need to know which driver is doing it, which vehicle is being done, etc. So without sharing the raw user data, we can always do this. And you can do what is called the local training. As I said, if you have a bunch of vehicles running in airport, yeah, and if you see a specific trend, you can always, based on the driving style, infotainment, the customer usage, etc., the driver behavior, etc., you can always customize that particular vehicle running in that particular segment. Okay, as I said, security is going to be a big challenge, because when you are asking for OTA updates and when you are asking for feature on demand, you are necessarily allowing access to the vehicle, allowing access to a specific app, etc. Even in, let's say, you're flying, whether you're flying through Indigo or Air India or SpiceJet or anything, even to check in, even to purchase a ticket, even to select a seat, you are agreeing to share your personal data, whether it is your first name, last name, date of birth, Aadhaar card number, credit card number, etc. As basic as that, you are allowing that information to be shared, so that the data privacy is protected, but at the same time ensures that the data is not leaked. So that is also being done. So what you do is you can use this particular federated learning-based hyper-personalization to look at multiple use cases, whether it is an adaptive infotainment, or whether it is personalized ADAS tuning, or climate control preferences, or driver coaching. For example, if some drivers are aggressive and if some drivers are passive, how do you make sure that you coach them? And of course, insurance. If some of the drivers are very aggressive, the insurance premium has to go higher. And if some are much more safer drivers, then the premiums have to go lower, etc. Some of these things also could be wanted. Then essentially, when you look at the workflow, this workflow could go through multiple steps. You can do what is called the initialization phase. Means when you are looking at the data, you are understanding the data, you are collecting the data, you are segregating the data, you are segregating into structured, unstructured, etc. And of course, you are doing what is called the bootstrapping of the vehicles. Means each SDV initializes which a base personalization model with respect to comfort, sport, economy, etc. for a specific vehicle. Just to give an example, this could be different for different vehicles. And of course, the local sensors, for example, collecting specific driver data, steering patterns, infotainment users, etc. As I said, user profiling, you are able to collect this particular data. Then you are trying to preserve the privacy and then do the computing environment. Okay. Then you are trying to do what is called the feature extraction. This is where you are doing the local model training. As I said, this data is not transferred to the cloud. The data is preserved on the vehicle. The data is used to train the model on the vehicle locally. So the feature extraction is done, the model update is done, differential privacy is done, means there is no data sharing to any other vehicle or any other cloud. Then the encrypted transmission, wherever it has to be transcripted, it will be encrypted primarily with respect to model update, not the raw data. Raw data is never shared. Okay. So the data privacy is assured every single time, and only the encrypted model updates are shared with the OEM cloud. So that is how the model updates are done. Okay. So in the cloud, what you see is essentially there is an aggregation server that collects the encrypted model updates. Let us say there are 100 different vehicles. Each vehicle sends the model. So there is an aggregation server on the cloud that collects the different model updates. Then from all the participating vehicles, then it does what is called the federated averaging. Means it combines the updates to refine the global personalization model. So it takes the inputs from a bunch of different vehicles, then it does the averaging, then it updates the model. Then the model again is sent back to each vehicle for what is called the model validation. The validation are again checked for safety, performance, regulatory benchmarks, etc. As I touched upon automated compliance in the previous slide. So whether it complies with the regulations, whether it complies with the standards, etc., that is also being checked. And as I said, if using digital simulation, you simulate the model behavior across what is called the synthetic driver profiles. Means before you send the model back to the actual vehicle, you can check on the cloud itself how this is going to perform. So digitally, you can do the simulation, and if you are happy with respect to performance, safety, etc., then you can release the model and you can send it back to the vehicle. And that is how this system, this goes through iteratively. For example, the 1, 2, and 3 iteratively go through multiple times so that the model is finalized, model is updated. Then if you have to release, then you do what is called the over-the-air redistribution and personalization. Okay, this is where there is an OTA update manager on the cloud, and it communicates with a specific app or a interface on the vehicle, and that is how the OTA update is done. Okay. So as I said, governance and compliance. You have what is called the audit logging. You know exactly what kind of models are being updated, which kinds of vehicles are being updated, etc. You have a very clear logging, because as I said, software bill of materials (SBOM) is very, very important to ensure your ecosystem, who's doing what kind of audit logging is done, what kind of changes are being done, etc. So SBOM compliance is very, very important. And of course, the regulators. If the regulators want to look at any specific a challenge in a specific vehicle development, they should be able to access the data, and it has to comply with ISO 26262 with respect to functional safety, with respect to UNEC WP29 on the cyber security, etc. So some of these things have to be complied. And of course, the policy enforcement. So let us say you are selling a vehicle in India vis-a-vis, let us say Sri Lanka vis-a-vis, let us say Germany. So sometimes the policy enforcements in different countries are different. So the OEMs have to comply with the local policies. So they have to enforce that. So conclusion, the need for SDV development, trends in the revenues, vehicle sales and software releases, these are essentially evolving, and these are essentially driving the evolution of the architecture. And the software architecture, as I said, something very similar to your UPI, means it is going through stack by stack by stack, means layer by layer by layer. So hardware abstraction layer, then the hardware interface layer, then you have the middleware layer, then you have the software layer, then you have the application layer, then you have specific personalization layer, etc. So you have different layers in the stack, and that is how the software is essentially evolving. And if you have to achieve the full decoupling, means greater than 90% decoupling between hardware and the software, it is still a work in progress, and that is where the companies are working on adopting virtualization. Then container design and optimization, means with respect to managing the workloads on the cloud, managing the workloads on the vehicle, etc. There are a bunch of different algorithms and bunch of different tools in what is called the CI/CD tools, continuous integration and continuous development tools. So all these things are being pursued. And as I said, most of the things are being done virtually and through what is called cyber physical systems. Means if you are making a specific change in, let's say, in-vehicle infotainment system, how it is impacting some other system. So you are able to look at what is called the virtual ECUs, and you are able to simulate them by running the code virtually, and then you are able to check all of them before you release the software. And as I said, with respect to personalization, means data privacy, minimizing the cybersecurity attacks, etc. Federated learning-based hyper-personalization is being increasingly adopted to protect the data privacy and offer security and efficiency computing. Okay. So future work, how is this evolving? This is evolving towards what is called the SDV Internet of Vehicles. Essentially, you had what is called the Internet of Things. Now it is evolving towards SDV Internet of Vehicles. This is a architecture that you see from this particular reference. You are welcome to access this reference. It is available in the open domain. So this is how essentially what you see is integration of software-defined networking and Internet of Vehicles, and they are essentially segregating the control plane and the data plane, etc. So you are trying to segregate this from the what you are seeing here, so that you have essentially an SDV Internet of Vehicles architecture. This is how the system is evolving. Okay, and of course, cloud connected services these days through connected vehicles, etc. Lots of things are being done in the cloud. Okay, and that is where the ecosystem is also evolving. And something very similar to medical records, for example, personal health record, you have also what is called the vehicle health record, VHR, where if there is a maintenance history, if there is a service record, if there is a feature upgrades, etc. All of these things have to be captured for audit purposes, for what is called the digital passport of a vehicle. And this VHR essentially helps you understand how this vehicle is evolving over a period of time, and how the changes, etc., are being evolved over a period of time. So that is also being done. Of course, there are specific standards and regulations are also evolving in this particular speed. Thank you so much.
Thank you, sir. Thank you for your wonderful presentation. Participants, you have not raised any questions in the chat box. If you have any questions, you can just ask it. Will you be just doing it as early as possible because the speaker is having another commitment. Please unmute yourself and ask the question. Sir, I have a question. So what do you think? Yeah, what do you think as the as a academicians, what is the research perspective that we can just go with this particular SDV, sir?
See, as an academician, what you can do is you can look at coming up with algorithms, because you are able to work on algorithms in a university setup. You are able to ask your students to code the algorithms and then work with an industry professional, so that the grunt work could be done by the students, and students will also learn, the professionals will also guide them. So it is essentially a combination of industry institute collaboration.
Thank you, sir. So I think there is no further questions. I'll just, sir.
One.
Mohan. Yeah, yes, sir.
Yeah, go ahead,
One
please.
question. One question.
Yes.
Dr. Arun Sampath, you talked about few standards. There was a standard for cyber security 21434
Correct.
from ISO standard
Correct.
for the cyber security road safety that starts from the concept to decommissioning of a vehicle. The entire
Correct.
Chain will be taken care of. Just few comments from on that.
Yes, correct. I'm aware of that. I did not put it there, but yes, that is also correct. I mean, that need not be for the vehicle itself. As I said, this ISO
Yeah, it's an entire
is applicable in fintech. It is applicable in healthcare. It is applicable in SDV. It cuts across multiple domains.
ITS in a way, intelligent transportation system.
Exactly. Wherever you have data, wherever you have IT systems, wherever you have data privacy challenges or cyber attack challenges, etc., that specific standard kicks in.
So thank
So
you.
application could be, see, a cyber attack, data is data. You interpret the data as a temperature or a temperature of a patient or a temperature of a coolant in a vehicle, etc. But algorithm doesn't care, and cloud computer doesn't care. To it, a temperature is temperature. You interpret as a human that this temperature is from a human, or this temperature is from a coolant or an engine oil temperature, etc. But computer doesn't know. For it, a temperature is a temperature and data is a data. So that intelligence we have, that computer doesn't have.
Thank you, Dr. Arun Sampath.
Thank you.
Any further questions? Okay. So let me propose the formal vote of thanks. First, I would like to thank Dr. Arun, the speaker of today, for his excellent explanation. So he started with the biggest challenge, mentioning the biggest challenge of SDV as the data privacy, and he insisted in many of his slides. And also he just mentioned one thing, like vehicle sales revenue all increases, and also the software sales revenue also keep on increasing. And he mentioned about the Internet of Vehicles, which is the future work with that SDV. And also he just mentioned where Internet of Vehicles will be vehicles communicating with each other. And also he just spoke about the SDV market, about the different corporations like NVIDIA, Robert Bosch, and Tesla. And he also mentioned that Tesla has the lion's share on SDV market. And he mentioned in his presentation about the SDV levels, 1.0, 2.0, and 3.0. Then he just spoke about the vertical top-down hierarchical approach of SDV, and also the digital twins and cyber physical systems of this one. And he also told about the evolution, like before 2020, what we had the architecture, and between 2020 2025 we had the cross-domain architecture, and between 25 and 2030 we'll be having the quasi-central architecture, and after 2030 we'll be having a centralized architecture. So he just mentioned about that. And he was also talking about the TCS focusing on the digital twin and virtualization, and also on hyper personalization. And he mentioned about that is the future thing. They'll be concentrating on the automated compliance, vulnerability management, and also on other things. And he just
Madam, if you don't mind, to make your life easy, all this information is available in the open domain on my
Open.
LinkedIn.
okay, sir.
Every
So
single thing, whether it is a verifiable credentials, whether it is evolution of architecture, whether it is federated learning, whether it is cyber security, every single information that I presented today, it is available in the open domain on my LinkedIn. Thank you.
Thank you, sir. And he stopped with, at last, he just mentioned about the SDV IOV and also about the SDV connected cloud services. So thank you very much for your wonderful session, sir.
Thank you.
And I thank all the organizing units for jointly organizing this one. And I also special thanks to our speaker and I also thank the senior members and from our various organization units and also the participants who participated in this particular webinar. Thank you all. Have a nice day.
Thank you.
Sir, Mohan sir, you're on mute.
Yeah, thanks, Arun, for the wonderful presentation.
Thank you.
Thank you.
I will sign off, please. Thank you.
Yeah, thank you. I know that you are tied up with another meeting.
Yeah,
So,
I'm running a little late.
yeah.
Thank you.
Thank you. Have a good day.
Ma, have you stopped streaming, ma? Divya, stop streaming, ma. Okay.
No, unmute. You are muted.
Thank
Nice,
you,
sir.
Mohan sir.
Yeah, nice.
It's a wonderful talk you organized, and I just came fresh from ITS India Congress,
Oh.
so it is